Good morning.
Hi, everyone.
Hey, good morning or evening, depending where you are.
It's a good morning. It's in Saratoga, California.
Yeah, it's morning. You say something, Kishan?
Can you hear me?
Yeah.
Okay.
I guess we're waiting for Ahmad. There he is.
All right. See, everyone is here. Roel, you're here.
I'm here.
Great. Okay, so let's get started. So welcome everyone to another OCP TAP session. This will be call number 93. And we have Roel here from Atomicron. So Roel has been working in time synchronization domain since 2018, mostly on business development side. Starting at Arbiter Systems, he has been very involved in the synchronization of SCADA systems, as well as promoting the usage of synchro phasers in power and energy sectors in Europe. He has taken part in development of the IEC, IEEE 6255-18-1 standard on synchro phaser measurements, published in 2018. He started out as a convener of the Seeger working group, writing the technical brochure on time in communication networks, protecting and control applications, time sources, and distributed methods. Roel joined Furgo in June 2022 to bring to market Furgo Atomicron products as part of the diversification business, giving access to the highest possible accuracy using GNSS augmented timing worldwide in real time. So with no further ado, the floor is yours, Roel. So also let's the slide, see if that works. And
we are sharing.
Yeah, we are keen to learn about how we can get sub-nanosecond augmented on GNSS. So
interested by chance?
Sorry, say again?
Interesting. Yeah.
Live
Yeah.
now.
You want to send me the link?
Want to
You
throw it
see
up on the board?
Sure.
Dennis, you're talking.
Please mute your microphone so we'll have no excuse to have sub-nanosecond.
You see my screen?
Yes.
Perfect. All right. Thanks for the introduction, Ahmad. Let me get started. I see this is a bit different. All right. So quickly introduction on Fugro. Most of you don't know Fugro because we are very active in positioning domain. We are a geodata company. I work for the satellite position department, and we internally have customers that we serve in getting accurate positioning, and also external partners as well that we serve this to. To do this, we have owned for over 30 years a proprietary ground station network that currently encompasses GPS, GLONASS, BIDAR, and Galileo. We have GNSS services that are in real time, high accuracy, and I mentioned before global coverage. And we have a proven track record. We've been doing this for more than 30 years. We have a very high uptime. All this network has been available for a long time, and we're exploiting that into our timing business today. So just quickly on satellite positioning, as you can see, these are assets in Fugro that we currently provide positioning to. It can be very diverse. We use this position for geodata. By the way, we're about a $2 billion company, so we've been around for a while. We're not like a small startup just starting with this today. So I'll start on the technical backgrounds. How does it work? What can we do? How do we achieve it? So first on the product offering, the Atomicron offering we have today, I'll just put some claims out here, some specifications, as you may. So we claim to be able to get you less than 5 nanosecond accuracy to UTC 95% of the time. Very bold claim. We're very confident on it, though. We like to be challenged. So if anybody's like, yeah, a lot of people said that before, just go ahead, prove me wrong, call me up, and we'll set you up with a test system. On top of that, we can get a sub-nanosecond accuracy to the Fugro timescale. I'll get on that timescale a bit later as well, which is at least 10 times better than existing high-end GNSS receivers on timing. On frequency stability, we can get to lower than 1e to the minus 12 at 10 seconds 8F, and I'll show you that later as well, how we do that. On top of that, because we have a nice reference network, we also offer navigation message authentication, and we can actually give you traceability to UTC time reference as well, giving you an auditable, assured timing chain from source to client receiver. So how do we do all this? Let's start with the ground segment. So basically what we have is a lot of dots here on the Earth, white dots, which are our reference stations. And these are actually concurrently receiving signals, GNSS, from all the constellations. As you can see, one satellite is being received at multiple locations in the same time. We have about 100 of these reference stations spread across the globe. Again, they're operational and used for more than 30 years. They are there's huge redundancy as well. If one goes out, there's no problem. There's at least a couple other ones that will pick up the signals that we need to provide our service. We cover, again, GPS, Galileo, BeiDou, and GLONASS, all of them. Some people are interested in mostly in GPS, some in Galileo, some want to use all of them. Although GLONASS is a little bit used these days, of course. To give you an idea where these ground stations are located, here's an idea. You'll see them a lot around coastal areas as well, because we serve a lot of vessels that cross the oceans. As you can see, Russia is not served well, but again, we don't have any customers today in Russia. And even without that, we could actually serve position and time in this area as well. As you can see, a couple of these dots are black. This is a screenshot from a live view. That means these stations are out right now. Again, we have so much redundancy in the system that that's not a problem. And we just can continue running the way we should. So these ground stations, again, shown here on the map as white dots, they need to get data. So we collect the data and we send that to two control network centers that we have, which are located, one in Houston and one in Singapore. So geographically away from each other. They receive data from all the reference stations concurrently. So every data from all the satellites, all the information is being sent to these two network control centers. Again, geographically separated for redundancy. They're running fully independent software, which is developed by different teams. So they're receiving and putting out the same set of data, but calculated in different ways. Again, to get redundancy in the system. They have a very high uptime. Actually, these network control centers get higher than 99.99% of uptime. We claim 99.99% today, but that's actually limited to the next part of the system, which I will get to soon. So basically, these network control centers are supplying data to end user GNSS receivers. The data generated in these control centers are so-called PPP correction data and independent timescale that we make ourselves and authentication data. So quickly, a quick step back on PPP. Most of the people here are I think, timing people, not so much GNSS experts. So PPP stands for precise point positioning. Basically, when you have a GNSS satellite in the sky, the signal travels through the ionosphere and the troposphere before it gets to your receiver. In doing so, it's actually getting delays in these layers. And the precise point positioning approach is actually removing, we're removing ionospheric delay with dual frequency. We catch that, and then we communicate that to receivers that don't support dual frequency. We're modeling tropospheric delays, And by doing that, we can cancel out most of the tropospheric delays as well. And based on input from all the reference stations that we have, of course. And then the PPP correction data output is per space vehicle, per SV, precise clock corrections, and precise orbit corrections, and also timescale information in our case. And this output, the precise clock and orbit corrections, normally gives you sub-decimeter level positioning in a positioning application. And it can be used either in post-processing or in real time. But we apply this now to timing. So how do we distribute this data to the end user? So the NCCs through uplink stations are sending data to geostationary satellites, Inmarsat satellites. They beam down this data to any location on the Earth. Doesn't matter where you are, except for the North and South Pole. Because they're geostationary over the equator and they don't have very good coverage on the North and South Pole. But anywhere in the world, we can receive this data and we put it into the receiver. So we have 6 beams that cover the entire world. We only need 3, but we have redundancy in the network control centers. So one control center is serving 3 beams, and then there are 3 other beams from the other control center. And that way we have redundancy in beams and in feeds. If one of the beam will go out, there's a redundant beam in the same area that can actually supply the data to the GNSS receiver. Now, the good thing is most GNSS receivers today can actually pass through this data. It's L-band data. It's right below GPS L1. And you can concurrently receive it with the GNSS signals to your GNSS antenna. Again, anywhere in the world, and we can also deliver this data over internet as well through an N-trip stream, which is a protocol used for this type of data. Okay, so you get your data to the receiver. On the left, we have our tracking network, timescale. It goes through the air. We send the PPP corrections, authentication data, and our timescale. So then it gets to the receiver. So if you have a receiver module, a typical module that could receive this will have its GNSS RX part of the receiver that's receiving all the GNSS signals. Then it's also receiving this data from us over the L-band, or alternatively through N-trip. That goes into a Fugro software library that we plant into the module with the partner we work with. And that supplies PPP corrected data to back to the receiver, and also our timescale, and also NMA hashes. The receiver software picks that up and optionally combined with an external clock, it will give you an output and tell you how far you're off to the atomic run timescale. And it will also tell you if you might be spoofed or not. So on the spoofing, and because we have this reference network station stations in the world, we receive the data at different locations. It is really totally unlikely that multiple stations are being spoofed in the same time. So what we do is we cross-check between them, and then we send hash data to the end user. We compare that hash data with the local hash from the current GNSS observations, and that way we can see if somebody's being spoofed based on the navigation message spoofing attack. So if the hashes don't match, it's very likely you're spoofed. I say very likely because it's almost never certain that you are spoofed, but something is surely going on, and you might not want to use that satellite vehicle at that time. And that's also the receiver then decides to not use that satellite at that moment in time and try to continue running on the satellites that are still okay. The navigation message authentication we do on all 4 constellations. As you may or may not have heard about Galileo OSNMA. OSNMA is doing a similar service, but only on Galileo. It is a free service, but still is very limited. If people know about this, they could actually jam Galileo, and people could still spoof GPS, for example. Amada, should I actually look at the chat in the same time? Oh, sorry, it was just about mute, I see. All right.
Just like on the chat, I'm just asking
Yeah, I
Feng,
see.
please mute your microphone, and Carl as well. So we're getting a lot of noise back.
All
Thank
right.
you. Thank
Good.
you. Good.
Thank you. So I'll continue. All right, so I just explained a bit on how we do it. And by the way, if there are questions later, I gladly answer them. You can interject me as well if you want to. But now, okay, sounds all nice and dandy, but how do we actually perform? I think that's very important. And actually, I watched the recording of 2 weeks ago. So there's a lot of explanation on time and frequency and phase. And I actually, I don't want to say I stole this from Kishan. I saw Kishan, you're on this call. I actually asked permission to use this in a previous presentation. I think this is a perfect overview on how something is actually synchronized, and then you get a time alignment. And based on this, basically, we have a performance that we can show. Now, let me first look at the frequency error. So a lot of you might be familiar with Allen deviation. What you see in this plot here is an example cesium standard on top, and the Allen deviation looks something like this. It's a standard graph. In the same time, you see an example passive hydrogen maser in blue. In this case, it's a quartz hydrogen maser. It's not the best performance out there, but it's a good one. And in the same, you see here a free running oven controlled oscillator. As you may or may not know, in the short term, they're very stable. In the long term, they're not so stable. And the other one's the other way around. A hydrogen maser, for example, in long term is quite stable. What we've done is to test our performance. We have actually created a GPSDO, a GPS disciplined oscillator, using this very good OCXO oscillator. So in the next slide, you see what happens. In the beginning, still the OCXO is keeping its good short-term performance, still about, what is it, 30 seconds. And after 30 seconds, our atomicron service kicks in, and you get the stability from the signal we're sending to the receiver. As you can see, this line below here, and we've repeated this multiple times, it's performing in a similar performance as a hydrogen maser, passive hydrogen maser, and much better than a cesium clock. Of course, we are not doing any holdover. We can just give you the stability. Holdover is not something we do. We are still using GNSS. I know a lot of people want to get rid of GNSS, but there's still a lot of good uses for GNSS as well. In this case, we can actually give people local access to the very high performance and stability. What we've also done to show the performance is the following. What you can see here in what I think is blue, I'm colorblind, but I'm pretty sure this one is blue, is a high-end GNSS receiver, multi-constellation, multi-frequency receiver, and we plotted the output of the receiver over a period of almost 7 days. So this actually compared to a clock at a NMA in Norway. I actually see, I think Harold was on this call as well. So what you see here is over this period of time, you get an accuracy of about, well, this is pretty good, by the way, it's sub 10 nanoseconds. And it's good performance, but what we've done after that is we used the same data, and we processed it with our atomicron data, our corrections, and you get the performance in the middle here. So as you can see, the stability went up dramatically. In this case, it's let me see, it's a couple of nanoseconds over time. And this is just the performance you're going to get. And what you see here we can do this in real time. And I think that's the biggest difference up till now. You could get this performance with post-processed data. And actually, that's the way the BIPM is doing it today. They receive GNSS signals from all over the world, connected to very stable clocks at NMAs. And then they post-process that data to get the best measurements on these clocks. And we do that now in real time. On the next one, here's another shot I wanted to show you. What we've done here is there are 5 different hydrogen meses that we measured with our service. So basically, they're being compared against our timescale. And what you see here is that the stability of the measurement, because in this case, we can actually measure the performance of these hydrogen meses over time. This is 16 days, and the drift you will see here is mostly the drift. It's partly the drift of the timescale and partly a drift of the clock. But these kind of performance on measurements you cannot get with GPS normally. If you want to measure 2 clocks at distances, you would have to use two-way satellite time and frequency transfer or fiber optic. Now, of course, using White Rabbit, using fiber optic is also very nice. You can get probably similar performance, but it's not available everywhere, and it's quite costly for a lot of parties to use. And what we can do and what we can offer is actually available anywhere in the world at a relatively low cost. Another thing I want to show you is a real-time time transfer between 2 locations. In Darmstadt is actually the European Space Operations Center and the NMA in Brussels. What you see here is we make use of our timescale to transfer the clocks between the locations. We have plots here based on GPS, Galileo, GLONASS, and BeiDou clocks. In this case, our timescale falls out of the equation, so there's no influence or almost no influence from our timescale. As you can see, we can do time transfer easily at sub-nanosecond level. In this case, it's 2 days, and everything stays below about a half a nanosecond. This is a type of performance that we can do in real time. Basically, every second you get a new update. And that's something that hasn't been shown before. It's also very difficult to verify this performance because you need access to really good clocks. Luckily, there's information available freely to people, published information from ORB in Brussels, for example, who publishes this data in real time to the IGS. We pick that up and we process that in real time and we can plot it. Next thing is what we actually working on today and going to introduce soon. We use atomic runtime because it's based on UTC, and we actually want to give people access to UTC and also in different UTC realizations in the world. So we are installing UTC, let's say, reference stations, and we measure the performance of service against local UTC reference clocks. We lock the offsets for 24/7, which gives an auditable traceability to these timescales. We can publish these logs every day. Well, we can on demand. And we started to continuously process data from several NMIs, of which PTB in Germany, JV in Norway, ROAC in Spain, INRIM in Italy. And I wanted to add NIST here as well, because we did start with NIST. Unfortunately, it's not a contracted stream that we get from them, and the stream has been down for a couple of weeks now. But I bet that will be coming up again soon. And what we will start doing in the future is give people access in the receiver to offsets of UTC NIST or UTC PTB, for example, because what we've noticed is with the accuracy that we're getting today, referencing against UTC doesn't seem to be very useful anymore today. UTC isn't stable enough, let's put it that way. So we expect people in the future, if they want to get sub-nanosecond accuracy, that they're gonna reference to a local, either a very good local clock that they own themselves, or to a UTC, local UTC realization, like a UTC NIST or a UTC PTB. About UTC, a lot of people are very worried about our 5 nanosecond claim to UTC. So what we've done, and we've done this together with just a FirstNet in Norway, JV. What we've done is we took our real-time data, time transfer between PTB and Brussels, and we laid that over post-process data from BIPM between PTB and Brussels. As you can see here, it fits pretty nicely. The difference is shown here on the bottom, and over this 1 week time, the accuracy of our real-time realization compared to the PPP post-processed information from BIPM, we're performing very good. This is in 0.1 nanosecond scale. We've done the same comparing PTB with JV. You see though that there are 2 different receivers used here. Even with that, comparing our real-time solution with post-process data from BIPM, we're still well within half a nanosecond over 7 days. And that's just showing the performance. This is a published paper, by the way. I guess in this case it was a poster that was published at ITSF. If anybody's interested, I can share this data. Okay, then results on the spoofing testing and NMA. We've done some testing in January last year. We did this at Fraunhofer in Germany. Let me walk through this a little bit. Here on the top, you can see the signal. Signals are normal here, and then from about here, spoofing starts, and they return to normal in the end. What we've done is we first look at Galileo as well, Galileo OSNMA, so the public free service from Galileo. Anything blue is authenticated, so spoofing starts here. And this is about, I think, 200 something seconds later. Galileo OSNMA detects that spoofing has started, and it will let you know that signals are not authenticated anymore. What we've done is we also show all the satellites that we authenticated below here. So BIDAL satellites, Galileo satellites, GLONASS, and GPS. Spoofing started here, and spoofing started on all 4 constellations. In this case, we detected the spoofing after about 100 seconds. It still takes some time. First on GPS, then on Galileo, even earlier than OSNMA did. Then we got it on BIDAL as well, and then on GLONASS. The reason for this is that today we're updating the spoofing data every minute, and that is, in this case, it was first GPS, then a minute later Galileo, a minute later BIDAL, a minute later GLONASS, and then after every 4 minutes, all constellations are updated. We will improve this actually. So the next iteration this year, coming out this year, all the constellations will be updated every 30 seconds. So if the spoofing starts here 30 seconds later, we would have detected it. Okay, then also that was spoofing using NMA, but in the same in the same spoofing session, we also actually detected spoofing in the timing domain, and we can do it because of the high accuracy, pretty much. What you see here in the beginning, all the signals are spoofed. You can easily see that the 4 different clocks are offset. Then there's no spoofing, all the clocks are the same. Then GPS is spoofed, so GPS is offset. They're the same again when there's no spoofing. Then BIDAL gets spoofed, there's a huge offset. Spoofing goes away, Now Galileo and GLONASS get spoofed, and there are offsets to see in the time domain. So for anybody integrating this solution, they can actually use the time domain as well to detect spoofing. And the scale here is 200 nanoseconds. So the time jumps are pretty big in the spoofed scenarios. But with a regular receiver, I wouldn't count on detecting, in this case, for example, what is it, a 30, 50 nanosecond time jump, because that could just be the receiver itself. So with our solution, you can actually set the boundaries much stricter and detect spoofing in the time domain as well. All right, so that's a little bit about the results that we have. So what kind of applications can you actually use the high accuracy for? I got a couple of things listed down that we think of that it could use for. Of course, anything that needs high accuracy time or stability, and accuracy between lower than 1 nanosecond between any locations across the globe. Today, that's being achieved by White Rabbit fiber optic links. Now we can actually calibrate those links with our servers. We can also monitor those links. And when they're commercially not viable, because long distances, we can actually replace those links and use our servers to transfer time from one location to another. Also, traceability to UTC-K in real time, to use UTC-K as a reference, and the K could be NIST or PTB. This requires a receiver at the remote site. We're working on getting that in place. And we can also give you historic traceability, of course. But another thing that we can do, and that hasn't been able to do with regular GNSS today, is we can monitor the performance of cesium, but even hydrogen mesa clocks. In the work that we've done over the last 3-4 years on this, we've looked at hydrogen mesa clocks through our service, and we've seen them fail, or people applying wrong corrections to these clocks. And we've noticed it before they noticed themselves, because they don't have any good reference to compare against. Then, okay, how available is our solution today? We have currently 2 ongoing partnerships, and soon we'll introduce a third one. One is with Septentrial, who is a GNSS receiver manufacturer. So anybody buying today a MOSIC T GNSS receiver chip will get Atomicron out of the box ready. It's available since June last year. Of course, we offer this as a service, so there's a license fee involved in this, but the hardware is available in the format of a GNSS clock. And then also Meinberg introduced it at last ITSF. They have their GXL module, which can be used in the modular clocks, which supports Atomicron as well, which will give you for sure the authentication, everything. The high accuracy, not to the sub-nanosecond level yet today, but that's to be released in the future as well. I think that concludes it, Ahmad. I'm not sure if I was way too quick, or maybe there's going to be lots of questions, but...
Well, we have lots of questions, so I'll start with asking anyone on the floor. You have a question? Now, don't forget to unmute yourself.
There might not be any questions, who knows?
Okay, I'll start with one. So let's say you have the Septentrio's receiver.
Yeah.
What do you need to do for the antenna?
Well, it depends on the antenna you have today. A lot of antennas will actually pass through L-band. And if it passes through L-band, you don't have to do anything. If it does not pass through L-band, you have to replace your antenna with an antenna that passes through L-band. Cabling, everything can stay the same. I know in your case, you're also using fiber optic transmitters for the GNSS signals as well. I actually talked to Uber sooner, I think at ITSF. They have products for that today as well that also will transmit this frequency as well. So relatively easy, but yeah, not every antenna out there today will work. because if they're filtering very nicely below L1, they will filter out the L-band signal. In our experience, most of them actually pass through the signal pretty good today.
Ishan?
Thank you, Roel. That was really, really interesting. My question is, are you ever planning on looking at any of the regional satellite constellations? QZSS, for example?
Yeah, well, the thing is, one of the selling points of this is also because that is available worldwide. I think that's what we're focusing on today first. And I think QCSS, I don't think it will add much. It doesn't add anything to performance. It would just make it regionally available in that area. And I don't, today there's not a lot of business out there for us. If there's people in that area that are specifically interested in it, we can always add it. We have the reference stations. It will of course need development on getting that data over as well. But that's not something we use today, and not something on the agenda, to be honest.
Any more
Another one,
questions?
Kishan? Oh, that's an applause, I see.
Yeah, thank you. It was
No problem. I see a chat from Harald that they actually tested GNSS over fiber with the L-band data using Violite fiber modem. So it is available. If you use GNSS over fiber, you can use it.
Harald, do you want to add more insight on that? Harald doesn't have a microphone.
No, but I think just that fiber modem has a really broad frequency range. So I think it essentially takes everything from 1 gigahertz to 2 gigahertz.
Nice.
So yeah, and also some of the performance data that Roel showed has been published in the proceedings of the EFTF IFCS conference in Japan.
Yeah.
Last year. Yeah.
Thanks for that, Harald, for generating that data and publishing it.
Any more questions? So I was wondering, like, they're like this, like a whole metrology thing. I forgot from BIPM.
Yeah.
So are you collaborating with BIPM basically to monitor things, like basically moving on to something, let's say, better than paper?
Well, the thing is, BIPM is very traditional, of course, in what they will adopt as a technology. Since this is not really out there a lot yet today, they are aware that it exists. There are discussions about maybe comparing this with two-way satellite time and frequency transfer. We've actually done that comparison already a couple of times internally, and it performs about similar. So yeah, the question is for BIPM, what are they going to do with it? They're not going to replace the current way of determining UTC with this. They will keep doing it at least for the forthcoming years, for probably 10 years or so this way. One thing that is in our mind though is, I don't know if you're familiar with UTC Rapid. Normal UTC comes out once a month. UTC Rapid comes out more often. But it's actually, if you compare the UTC Rapid product towards the normal UTC product, it's much worse in performance. So if this would be used to create the UTC Rapid, for example, you could have real-time data and very rapid, because you get it every second basically. So for us, that's of course something we'd be really interested in. Well, let's say we've started discussions with the BIPM on that, but it's going to be a long process, and there's a lot of things, calibration things involved, and things like that as well, of course.
Absolutely. Just wondering, Nobu, do you want to ask anything related to that? If like I mean, do you guys have any collaboration with NICT or?
I actually I'm waiting for a feed from NICT. And I asked them when we were in Japan, I think already. I know about. I know. I think there were some firewall problems, which happens all the time when people want to send out data in real time.
Yeah.
So I'm waiting for an update on that.
Okay, yeah, sorry. Like Kishan or somebody was asking about, or including QZSS as well. And yeah, that's very interesting. And yeah, we should take part in, but yeah, we have many details that we need to do internally. So yeah, sorry for if it's sort of slowing the process.
It's not a problem. I've approached a lot of NMIs, and we actually recommend them to stream to the IGS. IGS is providing a real-time stream, and anybody could use then that data, and we'll just pick it up and real-time process it and display it in Grafana, basically.
Paul, you want to go next?
So, Roel, that was a really excellent presentation. Thank you very much. So you said a couple of things that caught my attention, particularly for the use case I'm looking at. You said referencing against a UTC clock is not useful. You have to reference to a local clock. And then you said something which was very closely related. You said you seem to see failures. And what we know is that all the failures cause issues when we try to use timestamps for doing other things in a data center. So this suggests that for our use case, which is local, say within a single data center, it may be better to not try and synchronize with UTC, but just to have a single high quality clock that you can use as a grandmaster. But that means you don't need an antenna either.
If you're just local and just your one data center needs to be synchronized, yeah, you don't need GNSS.
How about frequency? You might need frequency because you want to have, let's say, everything with the same tone, right?
So you need a very good clock.
No, I know, but again, a good clock cannot be synchronized. You can have the best clock, but you're off on your own. But you want to stick to a standard. So then when you say, hey, we had this, I don't know, whatever gigabit per second, blah, 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 there is some truth to it that your measurement.
Okay. So you need at least 3 clocks.
No, still, like you can have whatever, like fusion of clocks, and that doesn't mean anything. The information is important to come there if you want to have your measurement repeatable and relatable. So I'm assuming, we all talk about phase here, and I think Harold's work was also the frequency. That's why I'm assuming it was presented at the FTF. So perhaps I'd like to see also some numbers, let's say on the frequency. You're providing the corrections for phase. You get like nanosecond, all of this thing. There is a frequency as well that is.
You get the frequency as well. I showed that in the ADEF.
Yeah. So the ADEF is providing a good, let's say,
but basically what the service does there, it's just transferring that frequency from a very good clock somewhere else right to your receiver.
Yeah, but then you consider the same, let's say, clock that is somewhere else, very good clock, to be the same when you go everywhere, and then you get your accuracy from it.
Your stability, yeah.
You can have amazing 2 clocks, but each one of them over time starts wandering on its own direction, and that's the nature
right.
we deal with.
That's right, but I think, if you look, I was saying, by the way, that you shouldn't use UTC because UTC itself goes about 3, 4, 5 nanoseconds over time. If you look at the NIST time assemble that's generating UTC NIST, for example, that's very stable. UTC PTB is very stable as well, and you could use that as a reference. That would be your stable clock. Or you can build that yourself, but then you need the clocks that NIST has, and most people don't have that.
Paul, you want to add more to it?
Yeah. Sorry.
Yeah, just a quick one. It seemed I heard your statement: a good clock cannot be synchronized, and I recently got aware of this concept from Ahmed about synchronization. I should have known about it years ago, but I guess I'm a bit slow. It seems to me that synchronization is indistinguishable from entanglement, and entanglement is universal; it's everywhere. So I wonder if that's what we're facing, is the engineering limits of things that once they become entangled, you can only do between 2 clocks, by the way, not between 3.
I didn't think about the entanglement in this concept, but I will consider entanglement more like on the phase rather than the frequency.
Right.
I mean, fundamentally, all of it is the same thing. Yeah. Harald, do you want to add something?
Yeah, one comment on the use of UTC. I mean, UTC proper without any realization is only available in deferred time. So up to 45 days after the fact. So you really need a highly stable and predictable clock if you're going to use that for steering your clock. And most clocks are not like that. So I mean, UTC is very stable and it is the best time scale, but it's only available in deferred time. But if you're gonna
We lose you.
to some realization like PTB and then if you look at the data of UTC, PTB, UTC NIST, they typically are within a nanosecond or so offset from UTC and this will improve once the major labs starts using optical atomic clocks to steer their timescales. Then their timescales will become even more stable and predictable. And I think the interesting thing about what Atomicon shows is that this type of PPP timing service is a way to disseminate even more stable timescales that one anticipates from using optical clocks, and it scales much better than two-way satellite time transfer or White Rabbit. So that's I think that's an exciting prospect.
One more thing
And-
I
and-
want to just as analogy is like, you know, those those labs that they work on equipments with like analog specifically, like a lot of analog measurements and so on. They get once in a like twice in a year or once in a quarter, like another firm to come and calibrate all their multimeters, all their scopes, everything to some reference, right? And then anything that happens in that last quarter or something is basically carried out as like, okay, this was part of it, unless you see something terrible and you have to trace back and get everything off. So this is similar to what you're saying. Like, I mean, this is how it works with UTC, that like you always look 45 days in the past and you see how good it was. I mean, it's an after fact.
Yeah, but if you have several stable clocks and you compare them against one another, then you have some notion if anything has gone wrong. But
Yes.
but still the timing is sort of the fresh produce department. So it's and in fact the use of this type of service for time transfer makes it possible to monitor the state of clocks even if they're not located in the same lab. As if you had a fairly high quality counter comparing two clocks, but now you can do it with distant clocks.
I can actually show you that. What I have here is you see my screen, right?
Yes.
It's a Gravana display of several clocks in the world, actually, which we're getting data of today. So if you look at the list, I have Australia here, the NMA in Australia, Brussels, this is ESOC, Italy, this is Bosnia and Herzegovina. I'm sorry I got you out of here today, Harald, because I can show why, actually.
Yeah.
You can actually see today, if you look today, last 24 hours. Okay, Australia's got a very good clock. All the other ones are all in the bottom here. Australia today went up to about 7 nanoseconds in a day. So if I just take out Australia, you see why I took Harald out today as well, because this was Harald's clock today. And it could be data hour on our side. I'm not sure what happened, Harald. It could be a reset of the process. But...
No, it's not our clock, but
Okay.
it's unscheduled reboot of the receiver providing the data, and
That's
then
what I thought.
the PPP process will have to restart. Yeah, so but it's
I
clearly
took
an
that one out.
issue.
But
Yeah.
then you see all the other clocks here, and we actually measure these clocks with our service, basically. Let's put it that way. In 24 hours, under 5 nanoseconds. And one thing you can see here about transferring that time somewhere else is basically, let me take PTB and Bosnia and Herzegovina. So what Bosnia and Herzegovina is doing today, they only have cesium clocks. So they steer their timescale towards PTB, and PTB is a very, very stable clock. So what you see here is that they are able now to get to this accuracy over a day, which they were never. And I can actually show you, and I've had right here, because I've shown this to other people. This was UTC to UTC Bosnia and Herzegovina, published by the BIPM. Up till here, it was every day. It was like, every day, every published data, I'm sorry, it was like +5, -5. And they started steering to PTB here, so transferring the PTB clock into their lab basically, and their actually UTC realization improved by a couple of factors. And this is what we can offer also to commercial parties. You have a clock in your lab that you need, a very stable clock. You can transfer UTC NIST as soon as we have the available information from NIST. Or you can actually transfer another clock from somewhere else that you have.
So if you go back to the previous graph, so take Bosnia and Herzegovina also out. Just leave like your your strong players. Bring some more. Yeah, PDB. Bring some more that are like with the same variance.
PTB is one of the best, but they're
yeah.
all pretty good.
Just keep it here. Do you see what is happening? Like there is a sync between all of them.
Yeah.
And that is because your measurement is falling behind.
Yeah.
So it's so amazing. I love this, you know.
So what we do then, we do time transfer.
Exactly.
So I can say I want time transfer, and then our time scale falls out.
Yes.
So I just say I want time transfer between Italy and PTB.
Yes, now it becomes stable, yeah. Because your clock versus them is definitely, these are like standardization bodies, they're like high-end clocks. So they beat your clock, and then that's why you get
And there's still a limit here, of course. I mean, the range here is 380 picoseconds.
yeah, I mean, this is nitpicking, but this is the world.
You picked Roel, you picked Bosnia Herzegovina and not Italy.
Sorry, I picked the wrong one.
Yeah, because what you see here is yeah.
And what you see here now is drift between these two clocks.
Yes.
You don't see the time scale anymore, but they're drifting apart.
Yes. It's amazing. The world of picoseconds.
And this is in real time. If I show the last 5 minutes, this is updating in Grafana. It's updating every 5 seconds.
Yes. So let's see. Is there any more questions?
I can add a comment to that. So the data that Roel showed is simply a comparison of that type of time transfer capability against what BIPM is computing in deferred time, using the final corrections for mostly for GPS and lately also for Galileo satellites. But one of the issues here is and actually to get time transfer with an accuracy compatible with the performance of the system, then one really needs to have a closer look at how do we calibrate antennas, cables, receivers, and define reference points. If you really want to use the sub-nanosecond potential here, then it also requires a closer look at at calibration, because typically what BIPM recognizes is a uncertainty of, I think, 2.5 nanosecond for the best GNSS timing receivers used for time transfer. And so to fully sort of use the potential here, then one has to have a closer look at also the calibration of receivers. So
Yeah, and we've seen actually between receivers, we've calibrated some receivers or had them calibrated, and we've seen offsets between receivers straight out of factory of in a nanosecond range.
Yeah.
So
Right. Any more questions before we adjourn? All right. Hearing none, again, I want to thank the speaker. Thank you, Roel.
thank you
And
for the podium.
everyone else. And we'll see you guys in 2 weeks with a talk by Dan Biederman from Intel about precision time based data movement. I mean, we'll see like basically how data can be moved with the presence of precision time applications and so on. Great. Thank you
Perfect.
very
Thanks,
much.
Matt.
Bye, everyone.
Bye.
bye.
You.